Hello, EP Chem. Today we're continuing with notes from section 7.10 through 7.12, and we're specifically dealing with solutions here. So first thing we want to talk about is saturation and equilibrium. For a saturated solution, that means that the solvent has basically taken up as much solute as possible at a given temperature, and some solid remains at the bottom. So specifically here, we're talking about liquid solutions. Remember, solutions can be gaseous and solid as well, but typically with these, the examples are going to include liquid solutions, usually where we're dissolving salt in water. So remember, the solvent is present in a higher concentration, typically water, and the solute is present in a smaller concentration, and that's typically a salt. At equilibrium, a saturated solution is saturated. So, or at equilibrium, a solution is going to be saturated. So if it's undersaturated, hasn't taken up as much solute as possible, that means that we have not achieved equilibrium in the solution quite yet. This is an image that kind of depicts what equilibrium looks like. So we don't just have solid particles sitting stagnant at the bottom and then aqueous particles in a solution. What's happening is we have two reactions occurring. One is the solidifying of aqueous ions back into a solid, and the other is dissociation of solid particles into their aqueous ion components. So it is a process that keeps going. It's not just sitting there. We don't just have some ions in solution and some in solid. They're kind of going back and forth. So it is dynamic. So this kind of depicts that we have a solid salt at the bottom. Some salts are dissolving into their aqueous components, where some aqueous components are going back into a solid. We've reached equilibrium once these two processes are happening at the same rate, which occurs when a solution is saturated. We have something called the solubility product constant, Ksp, which is kind of like the equilibrium expression for a solution. It's for usually ionic compounds in water. Like I said, there are different types of solution, gaseous solutions and solid solutions as well, but Ksp typically is used for ions being dissolved in water, your typical solution that you usually think of when you hear solution. So here we have two examples, calcium carbonate and lead 2 chloride. Calcium carbonate, when it's dissolved in water, forms two ions, Ca2+ and CO3 2-. The Ksp can be calculated using the concentrations of Ca2+ times the concentration of CO3 2-. We do not include solids in the Ksp expression, just like we don't for the equilibrium expression. For PbCl2, for every 1 mole of PbCl2 formula unit, which is like molecule for a salt, that dissolves, we get 1 mole of Pb2+ and 2 moles of Cl-. So I always kind of relate this to an Oreo cookie because it's hard to kind of think like, how do you start with 1 mole of something and then end up with 2 moles of something else? So if you start with 1 Oreo cookie and you split it into its part, you end up with 1 white cream filling and 2 of those hard brown cookies that are, not the best part of the Oreo. So that's how you can end up with 2 moles of something from 1 mole of something. You're breaking up this molecule or formula unit into its components. So the Ksp value for this salt would be expressed by taking the concentration of Pb2+ and multiplying it by the concentration of Cl- squared, because we get 2 Cl-. And we know that from the subscript in the formula unit for lead 2 chloride. The Ksp, the solubility product constant, describes solubility to a degree for a salt. So in general, if we have a Ksp that is 1 times 10 to the -3rd to 1 times 10 to the -54, it's a compound that's considered insoluble, so it doesn't really dissolve in water that easily. Remember, our solubility rules specifically for AP chemistry is anything with sodium, potassium, NH4, or NO3- is considered soluble. It will break up in water. Ksp is going to be greater than 1 for all salts that are soluble, all salts that contain the ions that are listed as common ions for soluble compounds for the AP test. The equilibrium lies to the right for these compounds, so we have high concentrations of the ions, which tells us that it is very soluble. So there are two things we look at with solubility. One is the molar solubility, which we will get into with the notes later, and one is the solubility product constant, the Ksp. The Ksp can be compared between two salts to describe solubility, but we also need to consider how many moles of aqueous ions are being produced from that salt. So when you think about it, like NaCl produces 2 aqueous ions, but another salt could produce 3. So if they break up, like if you break up 10 NaCl and 10 of a compound that breaks up into 3 ions, 10 of those 3 ion salts would have more ions in the solution, a more concentrated solution than the NaCl. So it would be more soluble if all 10 of those things broke up. So there's a lot to consider, is what I'm saying with this. Ksp is not like the one all be all for solubility. So here we have an example. We have 2 Ksp values for calcium carbonate and lead 2 chloride. The calcium carbonate has a Ksp value of 8.7 times 10 to the negative 9, and PbCl has a Ksp of 1.6 times 10 to the negative 5. So I want to know which is least soluble in water. So the first thing I'm going to look at is the Ksp value. For calcium carbonate, it's 8.7 times 10 to the negative 9. For lead 2 chloride, 1.6 times 10 to the negative 5. This, for calcium carbonate, is smaller than the Ksp for lead 2 chloride. So based on Ksp values, that tells me that this is less soluble in water. I'm also going to take a second and think, well, how many ions does it break up into? Calcium carbonate breaks up into 2, lead 2 chloride breaks up into 3, but since this is a larger number than this and it breaks up into 3, I'm very confident in saying that calcium carbonate is less soluble in water. So usually if they only give you that information, it's good to go off of. But if this was a smaller number than this, I would then have to consider, well, this is breaking up into 3 ions, this is only breaking up into 2, so really who is more soluble? But since this is only 2 ions and it's a smaller number, I'm very confident that calcium carbonate is less soluble in water. And it is. It has a smaller Ksp value, so I'm confident in that answer. So now we're going to talk about solubility. So solubility is the maximum molar concentration of formula units, which again, formula units are molecules for ionic compounds that will dissolve at a given temperature. So usually it's described in units mole per liter. So for every 1 mole of lead 2 chloride that dissolves, we again get 1 mole of lead 2 plus and 2 moles of Cl minus ions that enter the solution. For a solubility of PbCl2, it's going to be equal to the concentration of Pb2+, since that's a 1-to-1 ratio between formula unit and ions. And it's going to be equal to 1/2 the concentration of Cl-, since for every 1 formula unit, we get 2 Cl- ions. And again, this describes the concentrations when the solution is saturated. So solubility kind of describes the concentration, whereas Ksp is like the equilibrium expression for solutions. So you can solve for Ksp given the solubility of a substance, and you can also use the solubility of a substance to find the Ksp, because both of these values relate to the concentration of the ions that are in a solution. The other thing I want to mention for Ksp, I forgot to mention this, if Ksp is a constant at a given temperature, as all constants are, these concentrations at a given temperature must always together make the product of the Ksp. So if we were to change the concentration of one of these at equilibrium, then the concentration of the other would have to change, because this is a constant. These products always have to equal that constant. Okay, So here we have an example with the solubility product constant, Ksp, and solubility. So the solubility constant for lead 2 fluoride is 3.6 times 10 to the negative 8 at 25 Celsius. Part A, we want to write the balanced chemical equation of what happens when we dissolve lead 2 fluoride in water. Then we want to write the equilibrium expression, which is the Ksp, the solubility product constant expression. And then we want to find the maximum molar concentration of the ions in solution and the molar solubility of the solution. So in this example, we are given Ksp, the solubility constant. We want to find the solubility of this salt, which is the maximum concentration at equilibrium. So here's your balanced chemical equation. It's simply a solid lead 2 fluoride compound dissolving into Pb2 plus and 2F minus. For the equilibrium expression, we do not include solid in the equilibrium expression, so it's just going to be the concentration Pb2 plus times the concentration of F minus squared. For part C, we need to find the maximum molar concentration of ions in the solution and the molar solubility of the solution. So we are going to notate molar solubility as S. Here we have the Ksp value that was given in the problem, 3.6 times 10 to the negative 8. The concentration of the concentration of Pb2 plus ions is going to be equal to the molar solubility because it's a 1-to-1 ratio between 4 millunits and Pb ions. And then the concentration of F ions is going to be twice that because we get 2 F ions for every 1 4 milliunit of lead 2 fluoride. So it's going to be 2S squared. When we multiply these together, we get 4S cubed equals 3.6 times 10 to the negative 8. Then we can solve for S, which will be equal to the concentration of Pb, and we get 2.1 times 10 to the negative 3rd molar, which is moles per liter. To solve for the concentration of F minus ions, all we have to do is multiply this value by 2. So it'd be 2S, which equals 4.2 times 10 to the negative 3rd molar. This slide kind of tells you how to compare Qsp and Ksp. So the solubility product constant is, of course, expressed at equilibrium. But just like all the other K values, we have a Q value that you can use to compare it. Q is for at any point in the reaction, whereas K is only at equilibrium. So if Qsp equals Ksp, we know the system's at equilibrium, and we know that the solution is saturated with as much aqueous species as possible. If Q is greater than Ksp, we know that there's definitely a precipitate that will form because the solution will proceed to the left. Okay, so we're going to be forming solid until equilibrium is established. And if Q is less than Ksp, we know that the reaction will proceed to the right. We will produce more aqueous ions in the solution in order to achieve equilibrium. Here we're predicting possible precipitates. So we want to find the Ksp value for a saturated solution of PbCl2 if the concentration of Cl- is found to be 0.0325 molar. Then we want to know, will a precipitate of PbCl2 form when 200 milliliters of 3.78 times 10 to the negative 2 molar NaCl is mixed with 100 milliliters of 2.45 times 10 to the negative 2 molar lead nitrate. Assume that the temperature of the resulting solution is the same as that from part A. So this last statement here tells us that we can use the Ksp value that we find in part A to determine whether or not a precipitate will form with these given solutions. Okay, so I'm out of time for this video, but we will jump right into this problem in the next video.